Thank you very much. And it is a great pleasure for me to introduce our first speaker today, Professor Peter Atkins, who is going to talk about the evolution of the atom. There will be time for your questions at the end of the session. So thank you, so please welcome.
Thank you. Oh, thank you. It all began, like most things these days, with a referendum. And the referendum in particular was Democratus. And if you know your Greek, you know that that means the choice of the people. So really, Democratus, on the basis of no evidence whatsoever, suggested that matter was discrete, that it consisted of discrete entities, which in due course, of course, came to be called atoms. His teacher was Lysippus. About nothing is known whatsoever, apart from the fact that he was, in fact, Democritus' teacher. And Democritus's ideas were absorbed into the Epicurean philosophy, who really ran wild with it. So regarding atoms of things that were sour as things which were prickly things, things that were liquid, were composed of atoms which were smooth and so could roll over each other, and indeed didn't stop at the material, but went on to have atoms also of the soul, which were particularly beautiful and long-lasting atoms. Of course, we can giggle, but these days, of course, there are echoes of this in our understanding of the nature of matter, that we know that taste and olfaction do depend upon the shapes, not of atoms, but of the molecules that atoms, when they congregate, actually form. And we know that liquids also are composed of molecules that don't interact with each other strongly, so in a sense are smooth. But they, of course, are molecules and not atoms. And of course, there's no such thing as the soul. It's very hard to create Democritus's argument. Aristotle tried to do it in a typical way that characterized the Greek thought about infinity. And of course, they simply did not understand the concept of infinity. And apparently, Aristotle's argument about the fact that there are uncuttable entities at the end of matter can be illustrated as follows. He said, okay, take a block of matter, cut it into bits, then take that, one of the bits, cut it again, cut it again, cut it again, cut it again, and do it forever, an infinite number of times. And so you end up with absolutely nothing. And then Aristotle said, well, having got to absolutely nothing, you can't actually reverse the cycle because you can't create the material object out of absolutely nothing. And therefore, this argument must fail at some point, and it fails by going to infinity. So actually, you have to stop somewhere, and therefore there must be matter must be discrete fundamentally. And of course, that's such a slippery argument that we simply wouldn't accept it these days. The Greeks simply did not understand infinity, and a lot of their muddle came from their misunderstanding of that. Lucretius, of course, is always mentioned in this story. Roman poet, a few hundred years later, more poet than scientist. So really, if you examine his writing, it shows that he's simply drawing on other people's ideas. And although it propagates the idea of atoms, it's really insignificant. Well, from 500 BC, or thereabouts, to really almost 2000 CE, mankind slept. Instead of studying what there was, namely atoms, largely because they realized that they had no way of studying it experimentally, and all they could do was think whimsically about atoms, they decided there was a much, the philosophers decided that there was a much easier thing to think about, that's something that actually didn't exist, but seemed to be all around you, namely God. So for 2,000 years, mankind ignored the atom, being too difficult, too remote, and studied, one might say, wasted their time on studying things that did not exist, and devoted all their time to the properties of God rather than the properties of the atom. So we have to jump forward from 300 or 400 BCE to round about 1700 of CE. And really the figures that now come into our story are Lavoisier and his wife. Of course, Lavoisier lost his head in the French Revolution. Marie, his wife, lost her heart to Benjamin Thompson, the British-American spy and inventor of the chimney, and indeed destroyer of the caloric theory of matter, of heat. So anyway, but the point of putting Lavoisier as the start of the modern era is that effectively he introduced the balance into chemistry and the study of the atom. And this is an extraordinary moment because at last numbers could be attached to matter. And as soon as numbers can be attached to matter, so you are in the world of the physical sciences, the quantitative physical sciences. And so it's quite extraordinary that a number can be attached to a metal. I mean, it is common these days to think in these terms of the mass of something that is reacting or the mass of something that you're using. But this attachment of numbers proved to matter turned out to be the crucial step in our understanding of the atom. And indeed, it overcame the problem that the Greeks had, that they had no way of experimentally exploring atoms. We, through the use of the chemical of the balance, suddenly did. And so we're at the really the end of the 18th century before mankind woke up and started to deploy an understanding. And of course the arch deployer is John Dalton, who really by analysing results obtained from weighing reactants and products in chemical reactions, came to the conclusion that really one could talk about discrete entities, and that these discrete entities, these atoms, were left unchanged in chemical reactions. Of course, many people thought at the time that this is simply an accounting device, and that atoms were not real. They're simply a kind of fiction that enabled you to do calculations. But now we know, of course, that we can effectively see them. Well, at least if you don't like the term see in this context, then we can actually create images of them. And so we no longer have to go through the kind of convoluted inferential arguments that Dalton had to go through. And we can now convince ourselves that at root, at least at the root of this level of discourse, matter does indeed consist of discrete entities, namely atoms. So really at this stage, we know that we've got atoms. And what I want to do now is to start to talk about the evolution of this well-established modern context. And incidentally, the idea that atoms were an accounting fiction survived right into the 20th century. And it was really only in the early days of the 20th century that the evidence was really decided to be overwhelming that atoms existed. Really as a late intrusion into our conceptual fabric. So I'm going to focus now on the atom, and later on this morning there will be, you'll hear even more about the innards of atoms, but I will set the scene for that really. And we're now speaking of right at the end of the 19th century, 1897, for J.J. Thomson's discovery that there were electrons inside atoms, and that so atoms, hitherto thought of being uncuttable spheres, now had an internal structure that it was important to identify. So really, Thomson had this idea that an atom was like a blob of positive substance with electrons scattered inside it, the so-called plum pudding model of an atom. He had to think of, he had an idea of the mass of an electron, which was far, and knew the mass of a typical atom. And so it's because electrons are so light, thousands of times less than the mass of an atom, he had to presume that there were thousands of electrons inside an atom. So I've represented it really right like that blob with smallpox or measles. I mean, he tried to formulate this model quantitatively and got as far as thinking, well, I can do it with 4 electrons. I need stability in this atom. But so he could think of these 4 electrons moving in a circle, and was able to show that such an arrangement could actually be stable. But of course he forgot something crucial, that if you've got an accelerating charge, then an accelerating charge radiates. And so this model is inherently unstable because the energy will be lost from the atom. And this array, he could only do for 4 electrons anyway. And he knew in his heart, if not in his mind, that he needed to show that even thousands of electrons could persist in a stable way inside this blob of positive stuff. So, the problem didn't go away. I mean, how could an atom persist? The presumption that was made at the time was that the loss of energy by the generation of electromagnetic radiation would be extremely slow. And so this atom might last for millions of years, because the generation of electromagnetic radiation would be very weak. But no one really believed that, and it was a real problem, because such an atom cannot be stable. Similarly, at about the same time, the Japanese physicist Nagaoka came up with what is known as what he called, or what is called, the Saturnian model of an atom, in which, once again, thousands of electrons circulate like the rings of Saturn around this planetary blob of positive charge. But he sort of knew in his heart that this couldn't be stable, and indeed we know for similar reasons as for the Thomson plum pudding model, that it can't be stable because it would radiate. The crucial next step, of course, was right at the start of the 20th century, when Ernest Rutherford started shooting alpha particles, that is, helium nuclei, although he couldn't call them that, at atoms, and found that, of course, they went through, as they would on either the Nagaoka Saturnian model or the plum pudding model of Thomson. But just occasionally, one came back and bounced back from this sheet of this thin film of gold. And his conclusion, of course, is that that really an atom consists of a nucleus which contains most of the mass of the atom, with circulating electrons. So this identified the nuclear model of the atom, which of course is the core to understanding its structure and still is our model today. That, of course, was made quantitative by the newly emerging quantum theory of matter by Niels Bohr, who simply proposed, and it's rather in a kind of Greek way, that there were stable orbits with an electron circulating around the central nucleus, and that these orbits were simply stable, and he left it at that. Of course, he was able to render this model quantitative by invoking the emerging quantum mechanics. And it must have been thrilling for him to arrive at a formula for the energy levels which exactly, more or less, almost exactly matched the observed energy levels through spectroscopy. And I think that must have been one of the most thrilling moments in the scientific endeavour, to arrive at a complicated formula, plug in the numbers and find that the numbers agreed almost exactly with what was being observed, despite, of course, being wholly wrong. And the reason why this model gives exact numbers but is wholly wrong has very interesting foundation, which I shall come to later on. But of course, it's a dreadful model. Everything is wrong about it. And if you simply Google models of the atom, which I did, what you get is all this nonsense. I mean, it's such a powerful image to have an electron buzzing around a central sun that once you've seen it, you can't let it go. I think, I mean, this is just a random collection of images from Google. I think the best thing for it would be something like that. because it is so powerful an image, yet completely wrong. And we've got to go into its wrongness in order to arrive at today's perceived rightness. Of course, after Bohr came Sommerfeld, who generalized the totally wrong Bohr model into the totally wrong Bohr-Sommerfeld model. And it's wrong even more than the Bohr model. First of all, he allowed for elliptical orbits, as you see. And, fair enough. But he excluded the extreme elliptical orbit, namely that one, the straight line. Now, it will turn out, as you will see shortly, that one of the most important so-called orbits, and I'll refine that term very soon, is that straight line one. So not only is it wrong to think of electrons circulating in orbits like that, he also excluded the one that really matters, and I'll explain what I mean by that very soon. And of course, one of the things that the Bohr-Sommerfeld model gives rise to is that common perception that an atom is almost entirely empty space. If you look at this, then clearly that is true. I mean, the size of an atom has been likened, or the analogy that is often used is that the size of an atom is like the size of a football stadium, and the size of a nucleus is about the size of a fly at its center. Fair enough. And therefore, the inference is that the atom is almost all empty space, with just this electron fluttering around inside this almost completely empty stadium. You'll see that that is not true, and atoms are not all empty space. But we need to go on to how am I doing for time? This. We need to go to the founders, the introduction of what we could call modern quantum theory, quantum mechanics, in about 1927 through the work of Werner Heisenberg on an island, and Schrödinger up a mountain with a mistress, and Dirac in a world of his own. But I'll focus on the Schrödinger approach to the modern description of the hydrogen atom. In order to know what goes on inside Schrödinger's head, of course, we have to open it and see. And really, a bit of quantum mechanics that you need in order to just talk about. Well, I'll come to that in a moment. The image that finally emerges from solving the Schrödinger equation for a hydrogen atom and its generalization is that there is a distribution. I'll take away the boundary surface. And you can see that there's a distribution represented by the darkness of the shading of the distribution of the electrons. So there is the modern picture of the ground state of a hydrogen atom, with the electron clustering around in terms of its probability density distribution, clustering around the central nucleus. Why is that the structure? Why is that the ground state of the hydrogen atom? You need to know two things about quantum theory. And I know that many of you will be experts, but I know that also many of you are not experts. So let me just remind you of two features of quantum mechanics that you need to know in order to understand why that is the structure of the ground state of the hydrogen atom. One is that effectively the kinetic energy of a particle in quantum mechanics is determined by the curvature of its wave function. So if you've got a wave function that is not very curved, then that represents low kinetic energy. And if you've got one that is sharply curved, as I've drawn it here, then you have got high kinetic energy. I'm focusing on kinetic energy rather than linear momentum, because that's the focus I want to convey. The second thing, so in other words, high curvature is high energy, high kinetic energy. If you take the square of those wave functions, and here are the originals, and these are the squares, then the amplitude tells you the probability of finding something somewhere. So in other words, if this is the wave function, then there's a very good chance of finding the particle there, whereas there's very little chance of finding it there, where the square of the wave function is 0. So the density of the amplitude of the wave function tells you the probability of finding something somewhere. Now, think about that probability distribution I showed you a moment ago. You can, you can imagine different shapes, different ways, the rapidities of falling, of the probability falling away as you move away from the electron. If it's this blue one, it's sharply curved, therefore has high kinetic energy, but there's a high probability of finding the electron close to the nucleus because the amplitude is large at the nucleus. So that's got some sort of energy. Whereas if you take this one, comes out sort of green, then it hasn't got the same curvature. So it's got low kinetic energy, but the electron is likely to be, has a probability of being found far from the nucleus. So it has a high potential energy. And clearly there's a conflict going on. And the kind of conflict is that you can either have a small compact atom, which will have high kinetic energy but low potential energy, or the opposite, a big atom, where which has low kinetic energy but high potential energy. And there's a kind of Goldilocks region in the middle, which has the minimum. And so really what the Schrödinger equation is doing is looking for that minimum, that Goldilocks optimum shape of the wave function, and therefore the distribution of the atom. Notice also that because there's no curvature in going round, there's no circulation at all. There's nothing, whereas the Bohr model uses, if you like, centrifugal force to keep the electron away from falling into the nucleus. There is no motion around the nucleus. That's why, one of the reasons why the Bohr model is so wrong. It simply says you must have a circulation in order to get a stable orbit. But according to quantum mechanics, the ground state is one with no circulation. Also, notice that the distribution of electron probability fills the atom. There's no empty space, as there is in the Bohr model. It's filled with, admittedly, rather flimsy electron density, but nevertheless, it is not empty space. So there are so many ways in which the Bohr model is wrong, and the Schrödinger model seems to be on the right track. And of course, this is just the ground state that I've shown you. Once you start once you excite the atom, you can get more convoluted shapes. These are now sort of this is a 2s orbital, so-called. These are so-called 2p orbitals and so on. These do have circulation, but they're not the ones that correspond to the ground state. And you can get more elaborate distributions. So these are the so-called d orbitals of atoms, which show the distribution of the electron around the nucleus. And experimentally, one can even, although I don't understand really the experimental procedure used here, there are ways that purport to be a physical experimental demonstration of the kind of distributions of electrons that the Schrödinger solutions of the Schrödinger equation actually represent. Now, there's something very funny going on with the hydrogen atom, and I'm going to spend a little bit of time telling you funny things. You already know that there's something funny about the Bohr model giving you exactly the right numbers, even though it is fundamentally wrong. When things like that happen, you know that there's something interesting going on in the underground, as it were. Let's look at the energies of these orbitals that I've got here. Remember, I called them S and P orbitals. The energies are like that. Here's the tiny, fairly compact ground state, lowest energy state. This is the next energy level up with another spherical distribution, a bit puffed out a bit, and these three shapes showing different distributions. This has no angular momentum. These do have angular momentum around the nucleus. The funny thing is that these actually, as I have drawn them here, all have the same energy. That is, in the technical term, they are degenerate. How can it be that these four orbitals have exactly the same energy? Well, whenever you have degeneracy, whenever you have wave functions that have that look completely different but have the same energy, then you have to look for some symmetry. You have to be able to, it's pretty obvious that you can rotate that one into that one or into that one. So you can see that these are related by symmetry. So it's not surprising that they actually have the same energy. They're just distributions pointing in different directions in space. But how do you rotate that one into this one? Or rotate that one into this one? I mean, it doesn't seem to be possible to show that there is a rotation which converts that distribution into that distribution. The key is to understand the structure of the hydrogen atom, you need to think in 4 dimensions. I'm going to help you do that, so don't worry. If I were God, and who knows, I might be, and I strongly suspect I'm not, I think, and I wanted to give the universe the most beautiful potential function I could think of, I would give it the Coulomb potential function, that the potential energy of interaction of 2 charges goes as 1 upon the separation, 1 upon r, if you like. Obviously symmetrical in 3 dimensions, because r doesn't matter which way you're measuring your distance from the positive charge. The potential energy at a point simply depends upon the distance that you go. And so technically we would say that the Coulomb potential belongs to the group SO3, special orthogonal group in 3 dimensions. But it turns out that the Coulomb potential is not only totally symmetrical in 3 dimensions, it's also totally symmetrical in 4 dimensions. It actually belongs to the group SO4, special orthogonal group in 4 dimensions. That means that you might be able to find symmetries, for example, rotating that into that, if you step out a dimension. And because that's a bit difficult for you to imagine, it is for me to imagine, I'm going to take you into 2 dimensions. Okay? So I'm cutting out a dimension. And so I'll represent the problem as follows. I can obviously rotate this p orbital into that p orbital, no problem. Just rotate the square. But how do I rotate, giving it away, how do I rotate this into that? The thing to do is to realize that if you think in 3 dimensions instead of 2, then you can think of this colored sphere projected, think of a point there, projected through the surface onto a flat plane, and then color it with whatever it comes through. So if I project from there to the other side, it's that color. So in other words, I can see that I can get a kind of shape that I want. I can get that shape as well simply by rotating the sphere into a different orientation. And then I can rotate the sphere into this. And now you see I've got that 3rd shape. So if I am willing to step out a dimension and do my rotations 1 dimension up from what is obvious, then I can see that I can rotate into different seemingly unrelated orbitals into related orbitals. And you can practice. I mean, what shape do you need in order to rotate those? And the answer is you get something like that, which I can rotate, you see. So if you're willing to step out a dimension. So in other words, to understand the hydrogen atom in its modern guise, you really need to think of it in 4 dimensions. There's some more. Now, so far the hydrogen atom has only got 1 electron. The real problem, is when you've got more than 1 electron. And so the final piece of theory that you need is the so-called Pauli exclusion principle, which allows electrons to occupy, be described by orbitals, only 2 at a time. So you've got a kind of Noah's Ark, and you can fill orbitals this way, but that's it. But you can begin to see that maybe you get some sort of rhythm of the similar distributions, and that gives rise, of course, to the periodic table. Because we can now understand why there are periodicities in the properties of atoms, their ionization energies, their radii, and so on, and other properties, simply because we know how the orbitals of electrons are organized, and that we can simply distribute the electrons in them and get kind of rhythmical, cyclic replications of structures. I won't go into that because that's really chemistry, and I'm not here to talk about chemistry, and I've only got 30 seconds to finish. And I'll use those 30 seconds to say that, of course, I've now brought you to the point of the start of this year, which is the year of the International Year of the Periodic Table, if you weren't aware of that, and that it is the 150th anniversary of Mendeleev's publication of his periodic table. So I hope that in this talk I've taken you from the musings of the Greeks, unfounded as they were, to the substantial achievements of understanding the atom in its modern form. Thank you very much.
We have a few minutes for a few questions, so please. Yes.
Can I take you on your 30 seconds there? I was hoping you were going to get to, it's lithium, isn't it? Lithium has 3 electrons, is that right?
Yeah.
Yeah. So there's 2 s electrons and then another s electron.
There are 2 1s electrons and then a 2s electron.
And are you saying it doesn't really matter whether it's a 2s or a 2p, it's all the same thing?
Sorry?
Are you saying it doesn't matter whether it's 2s or 2p, it's they're degenerate and all the same thing?
I didn't go into because it's what you need to do when you're thinking of many electron atoms is you can't simply take the central potential from the nucleus. You have to allow for the interaction between the electrons. And so instead of the 2s and 2p all being the same energy, when you consider the interaction between the electrons that are present, then it changes their energies. And in this case, the 2s electron is lower than the 2p electrons. So it is the third electron goes into the lower energy, that is the 2s orbital. I should say that although we can solve the hydrogen Schrödinger equation, for many electron atoms you have to resort to numerical procedures. And so you can't get closed formulae, but very, very accurate ones nevertheless.
I didn't quite understand in the plum pudding and the other model why you had to have thousands of electrons. Was it because the mass was low and you had to compensate the mass? Why did it have to be thousands?
There was no idea about what the mass of the green blob was. It was known that the mass of an atom was such and such. And it was also known that the mass of the electron was 1,000 times less. So in order to account for the mass of the atom, not knowing anything about the green blob, you need thousands of electrons to make up the mass.
But if they knew that the electron was negative, didn't it have to be something positive as well?
That's the green blob.
Okay.
That's why I used red for the green.
Okay, we have another question there.
Hi. Over here. My question is that this has been fascinating to me, and I'm not coming at this as a physicist, it's just a fascinating lecture for me. So this periodic table, I don't know when we got to this point in the life of the atom, but just since then, with the emergence of all the modern physics that we've had now in the last 20, 30 years with colliders and all sorts of things, has the model changed significantly from this again? Or has it settled down on this?
Well, later on this morning, Sean, where are you? You're going to talk about that sort of thing, are you? You're going to split the atom later on.
I'm going to split the atom.
Yeah, so you'll see a real live demonstration of that. and that will answer one part of your question. But of course, I did mention Dirac in the course of this lecture, and what Dirac's contribution to quantum mechanics was to allow for relativistic effects. And so I decided not to go into that detail. The model of the atom is slightly perturbed by allowing for relativistic effects. But basically, we think we got it right, if that's really your question.
Thank you.
So I'm really going to pick up, and I'm interested in this idea of understanding the atom. So I completely believe we understand hydrogen, we have those extremely accurate. But one of the interesting things at the moment is still that some of the heavy element systems, we can't properly solve even numerically the quantum mechanics because there's so many electrons involved.
Well,
and there's still discussion, it's just unstable slightly, about whether we really understand the order of some of the levels and the sort of heuristic rules that we have.
Understand the principles of quantum mechanics. We might not be able to intuit them, but I think we can write down the Schrödinger equation, or, if you like, the Dirac equation for a many electron atom. And we can get as close to an accurate solution numerically as we want to. Now, all we'll get is a table of numbers. And whether a table of numbers or a graphical representation of a table of numbers is a form of understanding or not, I think it's edging towards it anyway. And then I think what scientists also do is not just leave it as tables of numbers. They ask themselves, why has it got this particular distribution? And in a sense, when I was talking about the competition between the kinetic and potential energies and looking for the Goldilocks energy, that's a way of achieving understanding at a deeper level than just a table of numbers or indeed just an analytical expression. So I think we are edging really towards understanding.
I have a vague recollection in Rutherford's first paper when he talked about the nucleus that he didn't assume that it was positive, or is that the correct recollection?
I think actually that's true. I think the challenge on the nucleus was ambiguous.
But he was able to infer, I think, the magnitude.
Yeah, so the Rutherford scattering of the alpha particles, you get the same answer if you assume the negative charge, the positive charge. So I'd curve that one, or we curve that way, depending on whether they're attractive or repelled, and the distribution of these particles, whether it's positive or negative, is actually the same.
Go into that later on, if you like.
We have quite a bit of time for one more question. Can we have please?
I'm curious, the quantum mechanics people, how strongly were they motivated in their exploration by that nagging problem of the radiative energy loss from the sort of billiard ball model, as it were?
Well, it was a problem that had to be overcome. And it was overcome by deciding that there were stable orbitals, no longer orbits, but orbitals, distributions of electrons. And then understanding the process of radiation. And quantum mechanical descriptions of atoms now also include the probability of transitions between these different electron distributions. So it was all part of the package of trying to overcome that problem and solving it.
Yeah, the previous generation seemed to have persisted for a while in, looking at different types of orbits and maybe speculating that the energy loss would have been minimal, so the atoms would have hung around for a long time.
Yeah, but what an atom has got to do is, in order to throw off what we would now call a photon, is to shake the vacuum. And if it can, when it, in a particular way, if you, I don't want to get lost into this, but if you've got an electron in, say, the 2s distribution, big puffy atom, and it collapses into a 1s more compact atom, there is no dipole moment associated with that. It's simply a spherical collapse. So it doesn't generate any electromagnetic radiation. Whereas if you've got one of those p orbitals, then you can reach an understanding of the process by which it is a dipolar redistribution of charge that occurs, and therefore you do get a photon thrown off.
Thank you.
Thank you very, very much, Professor.